Howdy, my name is Diego Macias. I'm a second-year PhD student at the University of Michigan, and I will be discussing developing a non-destructive method for characterizing holdup in liquid fuel molten salt reactors. So throughout this presentation, I'll be talking about holdup, and when I refer to holdup, I'm referring to fuel inside of your salt leaving your primary salt and being left on your salt-facing structural materials. And this can cause a lot of trouble for a molten salt reactor. The first of which, it can complicate your accountancy, because samples you take from your salt or online measurements you take may not be wholly representative of what's actually in your reactor, since your fuel is no longer in your salt. Another thing is, depending on where this holdup is occurring, you can increase the dose to your workers, and the fission products that are left on your salt-facing materials may end up altering their mechanical properties. And then finally, the increased activity in your structural materials may just increase the cost of decommissioning a reactor once it's reached the end of its life. So after the MSRE was completed, multiple components were taken out and were put under gamma ray spectroscopy. And one of the very interesting findings that they had was that deposition of fission products was non-uniform, particularly in the heat exchanger, which is what we have on this graph. They took a measurement of the activity of niobium as they went through the heat exchanger, and what they saw is, as they reached those baffle plates, they saw an increase in the activity of niobium. And so even when normalized for the surface area increase that was present at these baffle plates, they noticed that the activity was still much higher than like the smooth tubing in other portions of the reactor. So possible causes for this holdup include changes in flow and temperature conditions at different portions in your reactor. Impurity reactions with things in your salt can react with your fuel and end up leaving the salt out of solution that way. And then finally, local conditions and cracks and crevices can also present just areas where fuel will no longer stay in solution. So the project I'm working on is broken up into 3 parts. Where we currently are at is exposing components to static salt. And from there, we are measuring our detection response to these salt exposed components and using that to then go and measure holdup in a flowing molten salt system. And from there, we will use that data to train with a model and transform to be a more general solution for modeling holdup. So the non-destructive method we're using to measure holdup is densitometry. We take measurements of components before and after exposing them to static Flynax salt. And we look at our changes in our detector response and relate that to how much salt was left after we drained the component and how much fuel was left behind as well. These measurements are being done in collaboration with Georgia Tech and are being done by Jesse Bruner and Dr. Duji. So that's not me. So the testing conditions we're using to recreate holdup and deposition, we are currently exposing static tubes to Flynax salt with tellurium and europium. We're adding tellurium to our salts because it's a fission product of interest. We're really interested in seeing where that tellurium ends up. And we're using europium as our fuel surrogate for the time being. We cycle our temperature between 600 and 700 degrees Celsius, and we increase and decrease over 500 hours. So currently we're starting with tube geometries because it's a very simple geometry to work with. And then we're going to move on to heat exchangers in the near future. So after we've taken these densitometry measurements, our plan is to then do SEM and EDS, which is what we have here. What we have pictured here is a threaded rod that was inside of our sample. It was made out of stainless steel 316. And what we noticed is we have this chromium depleted area, but even more interestingly, our fuel surrogate, europium, was in this depleted area as well, which is very interesting to look at. And so the hope is that we can relate our densitometry response to the holdup we see in these destructive testing. So that way, when you actually are using a reactor, you wouldn't have to destroy a material in the reactor to see how much fuel is being held up. So future plans, we plan on continuing to do static tests, both with tubes and heat exchangers. We plan on using uranium-bearing salts in the near future to get a little bit more of an accurate representation of what might happen. And then finally, to investigate the changes in flow conditions and temperatures throughout a reactor, we'll be using a custom Copenhagen atomics pumped loop. We'll have about 100 degrees Celsius change in temperature across 2 heat exchangers, and we're really excited to see how that goes. I'd really like to take a quick moment to acknowledge the DOE's NEOP program for funding this work. And then special thanks to Connor Schamberger and MC Squared at the University of Michigan for helping me get all this together. Thank you all so much for your time.